Gottfried Wilhelm Leibniz was born on July 1, 1646 in Leipzig, Saxony, which is now Germany. He went to Leipzig University at the age of 14. He decided to go into professional service to noblemen, with duties including official historian and legal advisor. He had many different interests and made contributions to many fields. In engineering, he worked on clocks, calculating machines, and mining machinery. As a librarian, he invented the modern idea of cataloging. In physics, he made advances in the theory of momentum. He also worked in linguistics, history, aesthetics, political theory, and mathematics. However, because of his many different interests, he didn't complete most of his projects. One of Leibniz's greatest contributions was to calculus, as he is considered a co-founder of calculus, along with Sir Isaac Newton. We still use his notation today, including the d used for derivatives, from the Latin word differentia, and the integral sign, an elongated s that represents the Latin word summa. Through his discoveries, he eventually discovered the power, product, chain, and quotient rules for derivatives, as well as the fundamental theorem of calculus that derivatives and integrals are inverses.
Sir Isaac Newton was born on December 25, 1642 in Woolsthorpe, England. His father died 3 months before he was born, and his mother remarried 3 years after he was born, so she was left to live with his stepfather and left him under the care of his grandmother. The experience deeply impacted him, and as a result, he developed a deep sense of insecurity and would later anxiously obsess over his published work, defending it with all sorts of irrational behavior. In the early 1660s, he was convinced to go to Trinity College in Cambridge by his uncle. In 1665, the university closed due to the bubonic plague sweeping through England at the time. Newton was home for 18 months, and during that time entered the most productive period of his life. Legend has it that, at this time, Newton experienced his famous inspiration of gravity with the falling apple. According to the story, Newton was sitting under an apple tree when an apple fell and hit him on the head, inspiring him to suddenly come up with the theory of gravity. While there was no evidence that the apple actually hit Newton on the head, he did see an apple fall from a tree, leading him to wonder why it fell straight down and not at an angle. As a result, he began exploring the theories of motion and gravity. It was during this 18-month period as a student that Newton discovered many of his most important insights, including the method of infinitesimal calculus, the foundations for his theory of light and color, and the laws of planetary motion that eventually led to the publication of his physics book Principia and his theory of gravity. Newton came to calculus as a part of his investigations in physics and geometry. He viewed calculus as a scientific description of the generation of motion. At the time, it was easy to calculate the average slope of a curve, but the main problem Newton was struggling with was how to calculate the exact slope at any individual point on a curve. In other words, how to calculate the slope of the tangent line to the curve at a certain point. The idea is that the slope of a particular point can be approximated by taking the average slope of smaller segments on the curve, as the size of the segment of the curve approaches zero. Without going into too much detail, Newton calculated the derivative function, which gives the slope at any point on a function. This process is called differential calculus, or in Newton's terms, the method of fluxions. Having established a derivative function for a particular curve, it is now easier to calculate the slope at a particular point on that curve just by substituting in a value for x. The opposite of differentiation is integration, or as Newton called it, the method of fluence. Together, differentiation and integration are the two main functions of calculus. Newton's FTC states that differentiation and integration are inverse processes of each other, so that if a function is integrated and then differentiated, or vice versa, the original function is left over. The integral is thought of as the sum of areas of rectangles under a curve as the number of rectangles approaches infinity. Newton chose to not publish his newfound mathematical processes right away, as he was worried about being ridiculed for his out-of-the-box ideas. In 1703, Newton was elected president of the Royal Society. However, Newton never really seemed to understand the idea of science as a cooperative field, and his ambition and fierce defense of his own discoveries continued to lead him from one conflict to another with other scientists. In 1705, in a controversy that had been occurring for several years, German mathematician Gottfried Leibniz publicly accused Newton of plagiarizing his research, claiming that he had discovered infinitesimal calculus several years before the publication of Principia. In 1712, the Royal Society appointed a committee to investigate the matter. Of course, since Newton was president of the society, he was able to appoint the committee's members and oversee its investigation. Not surprisingly, the Royal Society gave Newton credit for his theories and credit to Leibniz for the first publication of the theories. As a result, Leibniz was accused of plagiarism by Newton and the Royal Society, causing an ongoing debate between the two mathematicians.
Here's an example of the FTC. If you draw a function
f of t, and you set the function on a closed interval from a to b, we will find the area under the curve and call it capital F of x. We will do this by setting a point x within the interval and find the integral from a to x, where x is between a and b. We will then put another value between x and b and call that x plus delta x. We will use the definition of the derivative to find the derivative of capital F of x using the point x plus delta x and find the limit as that value approaches 0. We find that this is equal to the area under the curve from a to x plus delta x of f of t dt, subtracted by the area under the curve from a to x of f of t dt, and we divide that by delta x. The MPT says that if there is a continuous function on a closed interval and if it is differentiable in the open domain, then there exists a value where the instantaneous rate of change is equal to the average rate of change. From there, we can separate the fractions and add a point C between x and x plus delta x, which represents the average rate of change as well as the instantaneous rate of change. That value is at the y-coordinate f of c. We can say that f of c is equal to the integral we found above, and therefore the derivative f prime of x is equal to the limit as delta x approaches 0 of f of c, which is equal to the original function f of x.
Regardless of who actually discovered calculus first, both mathematicians left a great legacy behind them. As Newton once said, "I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore, and diverting myself now and then in finding a smoother pebble or prettier shell than ordinary, while the great ocean of truth lay all undiscovered behind."